Okay, so I'll be giving two lectures, and mostly I'll be talking about power maps on finite groups of Lie type. Especially, I'll be talking about this particular topic for finite groups of Lie type, which is quite fitting to our workshop, and will make use of some of the things what we have done so far. Okay, so let me begin with. Okay, briefly describing you what is the plan for my lecture. So today I will begin with talking about finite groups of Lie type and the power map on that, and talk about one of the results to get asymptotic value for these ratios. Like I will define what kind of things we are looking for in the image set. Because in general, power maps are not surjective, so these kind of questions make sense. And in the next lecture, I will also talk about kind of a brief survey of what is known for power maps in general for various kind of situations like algebraic groups, Lie groups, etc. Uh, my plan earlier was to talk about that first, but I think uh, talking about the finite groups of Lie type will give you some good exercises to work for this tutorial. So I will talk about this first and then come to that later. Okay, so we have already seen what finite reductive groups means, but I will just quickly recall for uh, one reason that I want to set notations, and another is that it's good to revise. I mean things anyway. So FQ will denote a finite field, and K I will denote algebraic closure of FQ, uh, where Q is some power of a prime P, and G is supposed to be a connected reductive group over K, which is defined over FQ. So these things we have seen in lecture of Shripad, and I'm revising some of this stuff. Uh, and then you can use Lang-Steinberg theory to say that I have a Frobenius map F, this curly F or math frac F, so that the FQ points are exactly obtained by looking at the fixed points under that Frobenius map. Okay, so I can think of the FQ points of G as the fixed point of this Frobenius map on the group G. A priori, the group G, which I'm assuming here that it is a reductive group, and I will continue to assume that in my lecture, certainly today. Uh, so that is a priori defined over something like algebraically closed field K, and I can take the fixed point under F, and that gives me these groups of Lie type of FQ point. I will write GFQ. There is a reason why we choose this notation. Is this that I can think of the FQ points of G, which I denote by GFQ, to be sitting inside G. So I can go to algebraic closure for an element, and I can think of the elements there and things like that. So that's the advantage of fixing this kind of notation here. Uh, so this notation here I have written. So this notation. So this is the advantage of that. So this F is denoting here Frobenius map. Okay. So uh, so some of these things you've seen already. Now let's talk about the main uh, map which we are going to deal with, and we are going to deal with the power map. So I fix an integer m. Uh, m could be 1 or m is greater than equal to 1, and we know that whenever I fix integer, I can actually define a map which I call wm, which simply sends any element to its power x to the power m, right? And this is clearly a map which is a morphism of algebraic group. I mean, G is an algebraic group here, so this is clearly a morphism you know. So not just that, this map is defined over the field FQ. Keep in mind that I am always thinking of my situation K, where K is FQ bar, and I have the field FQ. So I have G here, and then I'm thinking of G is defined here, so I will think of FQ points. Okay. So I have the power map, which sends every element to its mth power. Uh, we have seen with some examples which we have calculated even in tutorials and otherwise, and we have seen also in Kuniawski's lectures, that the field plays a role in dealing with word maps, and hence in particular even for the power map, the field plays a role. Some things might be true her algebraically closed field, but it may not be true her other field. So we are particularly interested over finite field, right? So which gives me finite groups of Lie type. So yeah, so under this map, I will also denote. I mean, this is the notation I'm setting here. Uh, that GFQ to the power m is nothing but the image of this. So I can think of the map I have here, omega m. This also descends to the FQ points because the map is defined over FQ. So I will also, keep calling this map as WM. Yeah. And the image of this map, which is basically taking mth power of elements from GFQ, that in short, I will denote by GFQ to the power m instead of calling it like, think of this. It's just, longer notation to write. So this is more kind of suggestive. So I'll just use this notation. Okay. So some examples to keep in mind. We have already seen several examples of finite groups of Lie type, especially some examples of Frobenius we have already seen, and what kind of groups we are dealing with, we already know. So here are some examples. I'm just recalling these examples which we already done. So you can take the GLN over K, and on GLN I will define a Frobenius map, and the Frobenius map is defined by, let's say, the first I define this map, Frobenius map from GLN to GLN, which sends a matrix. So this is the matrix A. Let's say A is Aij, and it sends to, for each element I raise power Q. Remember, Q is the size of the finite field where we are working with. So I will send every element to Aij to the power Q. Right. So this is the map. And one can check this is a Frobenius map. And if I look at the fixed point under this map, we get actually the finite group GLNQ. So, I mean, often this is written as GLN FQ, or, I mean, notations vary, GLN FQ. In finite group theory, I mean, it's tradition, instead of writing FQ, just write Q. So the Q refers to this field here, finite field FQ. Yeah, again, it's just a notation basically. So I get the finite group GLNQ. I mean, with this kind of recipe. Whereas if I take another map which sends the matrix Aij to, so if I have matrix A, it sends to, so I raise every entry to power Aij to power Q, and I look at transpose inverse. So for transpose, I write T on the left hand side. Ryan Root was also writing T on the left hand side. So it's just to avoid, if you are using inverse and transpose both together, then it becomes confusing or to write the symbol. So if I look at this map, this is also Frobenius map. This is a Frobenius map. Okay, and if I look at the fixed point under this map, you will see that I will get elements which lie over FQ square, and I will actually get elements in the unitary group, right? So I think we have done these exercises earlier, but I'm just recalling that you can get this. There are many other groups like orthogonal groups and symplectic groups like ONQ, SP, uh, 2MQ. This kind of groups also you can get, and there are other groups like exceptional group G2F, Q, and things like that. I mean, there are many examples of groups you can get. Certainly, the corresponding to each simple algebraic group, you have this kind of groups. So all these groups you can obtain uh, over finite field, which is finite group of Lie type, using this kind of recipe. Okay, so this also helps you that whatever I'm going to talk about, if you are not very familiar with, or you are not very comfortable with reductive group or algebraic group, you can simply think about the group GLN or unitary group, yeah, or even SLN or something like that. Okay, so okay, uh, let me recall some more things. Again, these are done earlier, especially in the lectures of Shripad and other places. So what is a semi-simple element? In algebraic groups, we have notion of semi-simple element and unipotent elements. Uh, this is simply because this G algebraic group is a linear algebraic group. That means I can put it inside some GLN. I can put it inside some GLN, and I can think of an element which is inside this G to be a matrix, and then I can talk about semi-simple element. And a semi-simple element is nothing but something which can be diagonalized, right? That is the definition of a semi-simple element. And similarly, we can define unipotent element. And unipotent element is something that if I look at G minus identity, that is nilpotent. That is to say that G minus 1 to the power some M is 0, right? There exists such M. Then you say that such element is unipotent. So this is the definition of unipotent element, right? And that these definitions make sense, over base field also, in particular for the group GFQ. And in our situation, the way I said, you can always think of this phenomena happening over algebraically closed field, right? So an element is semi-simple if you think of it as over K, over algebraically closed field. There it is diagonalizable, right? So that's the definition of uh, more general definition of semi-simple unipotent over base field different. So these things make sense over field FQ, for example, here. In our case, for example, you can simply think of GK containing GFQ. And if I want to say that an element here is semi-simple, I will think of this element X in GK here, and there I will say that it is diagonalizable, right? And if you want to you want to think of the concrete example, then think of GLNQ sitting inside GLN uh, K. K is FQ bar, algebraically closed field. So if I want to say that an element in GLNQ is semi-simple, then I will think of this element over algebraically closed field over small k, and there it is diagonalizable, right? So all these notions of semi-simple, unipotent, all these things make sense over base field here. Uh, Interesting thing is that every semi-simple element belongs to a maximal torus, and this phenomena happens over the base field also. What is not true in general is that all maximal tori are conjugate over algebraically closed field over K, but that is not true over the base field, and we have worked out these kind of examples in our tutorials earlier. There are more than one maximal tori, certainly if you think of GLNQ, and but the good thing is that the semi-simple elements belong to some maximal torus. So why this is helpful? If you want to understand something about semi-simple element, uh, which could be much larger in number, whereas maximal tori are much easier to handle. They are kind of smaller in number. So you can work with maximal tori elements in the maximal tori, and that will allow you to that will allow you to work with semi-simple elements. In fact, we will make use of this strategy. So that's why I am emphasizing on this. And also, I'll just set this notation that if I want to take semi-simple elements in the group GFQ, I will simply denote it by GFQSS. So the GFQSS simply denotes this is set of semi-simple elements in GFQ. Okay, it's just notation. It's a subset of GFQ. Okay, I will also recall the definition of regular element. Uh, a regular element is supposed to be something of its centralizer is smallest possible dimension, right? So smallest possible dimension among all possible centralizers. So you take centralizer of various elements, and the elements which have smallest dimension centralizer, they are regular element. All this is work of Steinberg, and many of these definitions and all these things were done in the lectures earlier. Uh, also, recall that if I look at set of all regular elements, then they form an open subset. Okay, and if I look at a regular element X, and if I look at its centralizer, what is the smallest dimension centralizer possible? Can it be like very small? The result is that no, it cannot be very small. It is at least rank of the group G. For example, it is quite clear if you look at some nice element. So maybe, yeah, I have a blank page here where I can actually write down. So for example, the some of the examples of regular element is, let's take something like diagonal matrix. So I'm thinking of GLN, lambda n in GLN. Let's think of algebraically closed field for the moment. Then, if I look at the centralizer of this element, X in GLN, if you have ever computed this kind of thing, you will see that the centralizer depends on whether these lambda i's are repeating or not, right? So if lambda i's are repeating, it will acquire centralizer of that block size. So the smallest dimension centralizer will be achieved, which will be the diagonal matrices Dn when all lambda is a distinct, right? If, for example, I had first lambda 1 repeating twice like this, then its centralizer will acquire a block here, right? It will become a 2 by 2 block here, and then something like this. So it will be certainly bigger than n. In any case, Dn, which is the set of all diagonal elements, so this is diagonal. This is a commutative subgroup, right? It's an abelian subgroup. So if I'm looking at the centralizer of this element, lambda 1, lambda 2, lambda n, certainly it will contain Dn. It can contain more than that, for example, in this situation here, right? But it will contain minimum this. And the other example, which is the example of regular unipotent element, is you can think of, let's say, full size Jordan block. So this is a unipotent element. I'm thinking of n by n matrix. And if you look at its centralizer of U in GLN, this is something like, so one particular constant on the diagonal, then same thing on the diagonal above, and then something like this. I think this is the centralizer of this. And again, you will see that it is kind of dimension is n, which is, the rank of the group. So keep these examples in mind. So these are some examples of regular elements that they have smallest possible dimension. And yeah, so I said that if you look at the set of regular elements, they are open subset, and the smallest dimension for a regular element, its centralizer is at least rank. Uh, the set of regular elements in GFQ, that I will denote it by GFQRG. So this is a set of regular elements. That's the notation. RG will refer to regular element. Okay. Then we also have regular semi-simple element. So these are regular elements, but the ones which are semi-simple. So regular semi-simple is something of which, so we can simplify the definition in this case. A semi-simple element of which connected centralizer is a maximal torus, that is regular element. This is the definition. The first one is the definition for regular semi-simple element. And why regular semi-simple elements are more interesting. And in fact, I will work with regular semi-simple elements later. And this is the reason. The second one is the reason. Because regular semi-simple elements belong to a unique maximal torus. So if I understand maximal tori, then regular semi-simple element is exactly in one of the maximal tori. It cannot appear in more than one. Uh, you know, for example, if you think of uh, something like okay, what example I give? Anyway, we'll do it later in the tutorial. Maybe it's not a very difficult thing to think about. That if you are not regular semi-simple element, because it will acquire that 2 by 2 block, for example, if something is repeating in GLN, and that will say that it can belong to more than one maximal torus if it is not regular. So regular semi-simple element belongs to unique maximal torus, and will make use of this fact. The regular semi-simple elements of a maximal torus T form a dense open subset of T. Even if I look at one maximal torus and if I look at regular semi-simple elements inside that T, they form a dense open subset of that T. And combined with the fact that semi-simple elements are dense, it will also prove that regular semi-simple elements are dense in G. And we will see a I will try to give a proof of a version of this statement over finite field. Okay. So this statement makes sense over algebraically closed field where you have Cheresky topology and whatever. So then dense and something like that makes sense. We all understand that. But uh, there is a version of this statement over even finite field, and we will see that. What does that mean? Again, the notation, the set of regular semi-simple elements in GFQ, that will be denoted by GFQRS. So for regular semi-simple, RS. So just recall that I have GFQSS for semi-simple, then GFQ RG for regular, and GFQRS for regular semi-simple. Okay, good. So what I'm going to do here now is that let's get back to our main problem. We are trying to look at the power map, right? So we are trying to look at this power map at the level of GFQ, and now this has GFQ has this certain kind of subsets, the subsets of semi-simple elements, regular semi-simple elements, and regular elements, right? So I want to know whether I can get uh, one of these kind of elements in the image, right? So I will look at the image here. So the image of this is GFQ to the power m. This is a subset here in the image here. Now question is that does this subset here, does this subset contain a regular semi-simple element? Does this subset contain a semi-simple element? Or does this subset contain a regular element, right? Can I find something about that? Can I prove that, or I can ask that question? In general, the power maps are not going to be subjective here. So we have to look at a more refined version. We can ask about certain particular kind of elements, whether those kind of elements are there in the image or not, right? So for that, I'm going to set this notation here. The notation is that uh, GFQ to the power m intersected with GFQ RS, that I will denote by GFQ to the power m RS. Right? Similarly, GFQ to the power m intersected with all semi-simple element, that is denoted as GFQ to the power m SS. And similarly, I have GFQ RG to the power m. This is a regular element inside GFQ to the power m. So, what does this notation mean? Once again, there is another way of saying this. Uh, so there are a couple of things which I want to point out here. Uh, I am not looking at the image of GFQ RS under the power m. That is a slightly different subset. I also have option of looking at the set of regular semi-simple element and look at its image, right? But that is not what I am looking at here. I'm looking at the image of the power map, and in that image set, I want to see whether there are regular semi-simple elements. This is slightly different from saying that I will look at the image of regular semi-simple element. Yeah, so keep this in mind. And why this kind of questions are important in kind of combinatorial theory. Basically, this kind of questions are called uh, probabilistic questions. So, for example, if I look at, let's say GFQ RS, just set of all regular semi-simple element, and I look at the ratio with respect to GFQ, right? So this will say that this is what if I can obtain this quantity. I mean, both are finite quantity because I'm working with finite group. So whatever this quantity is, this will say that this is the probability of finding a regular semi-simple element in the group GFQ, right? This is probability of finding a regular semi-simple element. These kind of questions are important from combinatorial point of view or probabilistic group theory or computer science point of view. That whether you can, I mean, this kind of a subject in itself where people try to obtain this kind of results and also worry about algorithmic problems. So if I look at power m here, if I look at this quantity, that GFQ to the power m RS with respect to GFQ, the ratio of this, then I'm asking what is the probability of finding a regular semi-simple element which is mth power, or equivalently which has mth root. Remember, an element which belongs to this set here, GFQ to the power m, these are those elements for which I have mth root. I can, if I try to solve, so another way to look at this problem here is this, that that if I give you an element G here, can you solve x to the power m equal to G? So where G is an element in GFQ here. You can solve this equation only if the element G is in this image set, right? So this kind of ratio also says that if I take a G as a regular semi-simple element, whether I can solve that. So this is the reason why I'm talking about this kind of set. Okay, fine. So now I hope the notation is clear because it can get confusing otherwise. Okay, good. So what is the question I am going to deal with? The question I'm going to deal with is this, that I will look at these ratios of what I have defined, and clearly this ratio will depend on what is G, what is M, and what is Q, right? So the question I am going to ask, that if I take limit Q tending to infinity, whether it has some finite value, and what is that value? Yeah. In general, GFQ to the power M or GFQ, it's a polynomial in Q and something to do with M, and of course something to do with the group itself, of course. But can I say that this ratio will be finite? and what is that value, right? And we'll see that this is always finite, and all these quantities are equivalent, right? That is the result which I'll be talking about. So as I explained earlier, that this can be thought of as a probability of finding this certain kind of elements which are mth power. Uh, and Also, I want to clarify what is the meaning of limit here. So let me explain that. So when I'm talking about, uh, let's say I want to say that I want to look at limit q tending to infinity of uh, uh, g fq to the power m rs by gfq. So clearly these are finite quantity. So this is some real number, right? But this real number is going to, so I will fix g. So when I am going to work here, because I'm saying limit k tending to infinity, so basically I'm fixing g and fixing m. If I fix g and m, then for various q, I have these real numbers. So I'm looking at this set of real numbers, and I am looking at limit points of this, because I don't know whether whether the limit point exists, and I don't know whether the limit point is unique. This kind of things I don't know yet. Obviously, if m is equal to 1, uh, it's a classical result, which is what I will explain, the meaning of density, that these are all dense. So that will say that this ratio is 1. For m equal to 1, this ratio is 1, and it has only single limit point. Uh, but when m is not 1, which is what we are going to explore, uh, there could be more than one limit point of this set. But we'll prove that there are only finitely many limit points of this set, and how to obtain that value using the structure of G, using the structure of the group G. Yeah. So when I'm saying limit q tending to infinity, you can obviously worry about it, whether it is like, whether first of all limit exists or not, and whether there is only one limit. How do I know that? So what is the meaning of saying this expression that limit q tending to infinity is this? So in short, which I will keep writing, that I will not write this bracket, and also the limit q tending to infinity of this particular thing. And it will be given by a formula. However, the formula itself will take more than one value depending on the situation. So we'll be able to obtain a formula for this depending on the group G. Okay, so we'll see this. Let's go ahead and uh, so this is the result which I want to uh, 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 tell you. So again, just notation: G connected reductive group defined over FQ. M greater than equal to an integer. Actually, 2 is not necessary. M greater than equal to 1 is fine. Uh, and the result is this, that all these limit points, so again, these are set theoretic limit points, all these limit points are equal, and they're equal to this value. Yeah, so I have explained you the meaning of this and this, right? So I'm saying that all these quantities are equal, and they're equal to this value. Now what is this value? Right? So let's understand at least the meaning of the various quantities involved in this formula here. So I'm looking at sum over something, and the sum over something is that these are maximal tori, non-conjugate maximal tori up to conjugacy. Okay, the sum varies over non-conjugate maximal tori T in the group GFQ where we are working with, and this in the denominator I heard WT. So WT refers to the while group of that maximal torus, which simply means that you look at the normalizer of T in GFQ mod T. Okay. We've already seen that this can be also calculated going to algebraically closed field and taking the Frobenius fixed point and things like that. So we know all that kind of stuff. So it makes sense here, whatever I written. What is m comma d1? So this is supposed to be GCD of m and d1. M we know, m is given to us. What is this d1, d2, ds? So we are working with this maximal torus T. This maximal torus T is supposed to be something over FQ, right? So it's something finite, right? So what I do is that I write it as a product of cyclic groups, CD1 cross CDS. T is a commutative group, right? So if it is something abelian and it's a finite abelian group, it is a product of cyclic groups. So whatever the cyclic, write it as a product of cyclic group, and whatever this D1, D2, DS appear here, these are the D1, D2, DS used here, right? So we require the cyclic structure of maximal tori, various maximal tori. I mean, different maximal tori, because there are going to be several maximal tori. They will have different cyclic structure. So it will vary. D1, D2, DS will vary uh, with the maximal torus T. Okay, so I hope now everything appearing in this formula is clear. Let's work out one example. I think I'm going to write down an example first uh, before I go ahead and try to prove something. Okay, so I explained everything here in this theorem. So this is the theorem, uh, and so this work is, of course, collaboration with Amit Kulsresht and Jubrata Kundu, and it has just appeared in the Journal of Group Theory online, so you can check online. It's available there.
Anupam,
Um,
I have a small comment here
yes, yes, yeah,
that
yeah,
this decomposition into cyclic subgroups need not be unique,
yes, right. But
but
it
these
doesn't matter
product of
actually.
ABCD is still the same, right?
Yes, 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 yeah. It doesn't matter actually.
It doesn't matter.
Yeah.
Okay.
Okay. So let's work out an example here. Uh, First. So yeah, so I spent some time actually writing down first brute force method. This is the method which we have been using in many examples in our tutorial. So let's go through that first, and then we'll apply the formula and match whether we get the same value, right? Otherwise, we don't know whether formula is correct or not. So I will work with GL2Q. Remember that we are looking at the power map. Uh, Omega m from GL2Q to GL2Q, which means that it sends every element to its power m. All right. So, and we have seen that images are closed under conjugacy, etc. So, all I need to worry about, look at conjugacy classes. So, first I want to write down what are the conjugacy classes in GL2Q. So, the conjugacy classes in GL2, there are four kind of conjugacy classes in GL2Q. This can be just written down using the canonical form, rational canonical form theory. So one of the kind is what I call central class. So these are central element. These are of the form. These are of the form lambda lambda, where lambda is some non-zero element in the field, right? And how many such classes are there? As many as non-zero elements, right? So there are q minus one such classes. What is the size of each class? Because these are in the center, size is simply one. Yeah. Then the other diagonal class where lambda one and lambda two are different, that I call split regular semisimple. Is just a name, but obviously you know why this name. So there is a reason to this name. So lambda one, lambda two, where lambda one is not equal to lambda two, and they're non-zero element in the field. How many such classes can be there? Remember, if lambda 1, lambda 2 are different, they are different conjugacy classes. They're not the same conjugacy classes. So there are as many conjugacy classes as we can pick lambda 1, lambda 2 up to permutation, right? And this can be simply said that, so lambda 1 can be chosen in q minus 1 ways, and lambda 2 has to be something which is not equal to the earlier chosen lambda 1. So there is q minus 1 into q minus 2 choices. But I can choose lambda 1, lambda 2 up to permutation. So lambda 1, lambda 2, and lambda 2, lambda 1 are conjugate. And that's the only relation here. So I have to take half of that. So there are going to be these many conjugacy classes. And you can also calculate the size of these conjugacy classes. And to compute the size of conjugacy classes, I use, from finite group theory, we know that formula class equation. So that is going to be order of G by order of the centralizer. Centralizer of such a thing is the maximal torus, the diagonal maximal torus. So you can just substitute the value and you'll see that you get q plus 1 into q. Okay. So these are two classes, and two classes meaning like uh, there are q minus 1 here. So these are called types, actually, what I have given the name. But there are q minus 1 such conjugacy classes, and there are q minus 1, q minus 2 by 2 such classes. And then there is going to be what we call anisotropic regular, and these are given by degree 2 irreducible polynomial. And I think we already discussed in tutorial that there is another way of looking at this, which I particularly like, because this helps us to compute somewhat easily, uh, especially this kind of computation when you are looking at power map or things like that. So these classes correspond to an element in fq square over fq. Why is so? Any element of fq square, if you look at its minimal polynomial over fq, it is a degree 2 irreducible polynomial, right? So every degree 2 irreducible polynomial, in fact, correspond to an element here in fq, because there is unique extension here. You can think about it. So these are the one which exactly gives you this anisotropic regular element. Uh, uh, they are diagonal over the extension fq square, or if you go, of course, over algebraically closed field. And so how many such classes are there? As many as elements in fq square minus fq, right? Uh, of course, there is a pair theta and its conjugate involved. So fq square has element q square. Leave out elements of fq, q square minus q, and theta and its conjugate will give you the same element. So that is q square minus q by 2. And again, you can compute the class size by computing the centralizer and things like that. Centralizer is much easier here because minimal polynomial characteristic polynomial will be equal here. So we are seeing that it's just polynomial in that. So the centralizer will be just fq square star. Okay, fine. And then other than this, what is called non-semisimple class, where the representatives will look like lambda, lambda on the diagonal, same lambda, and one above that. And there are going to be q minus 1 such classes, which basically just lambda is varying. So there are q minus 1 such classes. And you can also compute the size q square minus 1. Very good. So let's yeah. So first I wanted to say what is m equal to 1 case. Now using that data, you can compute how many conjugacy classes are there. So you can just sum all of them. You'll get q square minus 1 conjugacy classes. Okay. Total number of element, that is just the size of GL2, so which is q square minus 1 into q square minus q. I have just written it here so that I can make some statement. Total number of semi-simple conjugacy classes. So first three classes are semi-simple. You just add them, and you will see that there are q square minus q semi-simple conjugacy classes. If I want to count the semi-simple elements, then I have to multiply each class with the size of the class and then sum it up. Okay. So then you will see that you get q to the power 4 minus 2q cube plus 2q minus 1. And similarly for regular semi-simple, this is the second and third class. That will give you q minus 1 whole square, and regular semi-simple element will come out to be q to the power 4 minus 2q cube plus q. So what is the statement I wanted to make here to observe? Suppose I look at the ratio of GL to Q regular semi-simple element divided by GL2Q. So GL2Q regular semi-simple, where is regular semi-simple? Regular semi-simple element. So I will look at this here. So that is Q to the power 4 minus 2Q cube plus Q divided by total number of element, which is going to be Q to the power 4 minus Q cube minus Q square plus Q. So you can see that highest degree power of q here is same. Even the coefficient is same. So if I wanted to take limit q tending to infinity, I can multiply. I can divide numerator and denominator both by q to the power 4, and you'll see that 1 by q will become 0. So I'll get actually answer 1. This is the meaning of density here. Yeah, the probability of finding a regular semi-simple element is actually 1. If I make q large, I mean, if you look at q small, maybe it will not turn out to be 1. It will be smaller than 1. But if I take large and large and large field, in the GL2 itself, probability of finding a regular semi-simple element is 1. This is what it means. And you can do the same calculation for semi-simple element, and you get, again, this is the q to the power 4. That will again give you 1. So this is the meaning of density. So I just wanted to explain you that here. And we want to find analogous formula for power also. I mean, if I can get a formula and if I can compute what is the probability, and it will not turn out to be one in general. And that is what the formula will tell you, the formula which I displayed you earlier. Okay, so let's try to compute at least squares, right? This is something which we have been doing. Uh, so I will just, I will write down here a short calculation which will just help me conclude. So there were class like lambda lambda, and if I square this, I simply get lambda square lambda square. And there was a class lambda 1 lambda 2. The square will be simply lambda 1 square lambda 2 square. Then there is a class which correspond to irreducible polynomial. I will think of over fq square, and this is just theta theta bar, and if I square it, I get theta square theta bar square. And then finally there is a non uh, semi-simple class. Its square will be lambda square. Here I'll get 2 lambda. So you notice that if characteristic is not 2, then this class will actually give you the non-semi-simple class, right? If characteristic is 2, then this will become 0 and it will become semi-simple. Um, and you also see that all semi-simple element, their square is again semi-simple element, right? It's clear? Okay. So now I'll just make use of that to quickly compute. Now I want to know, I will take element in the image in GL2Q and I want to know whether they have a square root or not, right? So if I look at scalar matrices, my claim is that all of them have square root. And the square root is nothing but the matrix of this kind. I mean, I've written down here. So if I take a matrix 0, mu, 1, 0, square it, I'll get diagonal mu, mu. So every element. So the thing is that you would have wondered that diagonal elements should come only from this. That's not necessarily true. It can come from this one also, the third class, which is coming from FQ square. Okay. Which split regular semi-simple elements are square? They are obtained by squaring element of the same kind. Again, you can go through that calculation above and say that. So how many elements are there? So these are only elements of the form lambda 1 square, lambda 2 square on the diagonal. So how many ways I get lambda 1 square? This is possibility of square in FQ star. Let's for the moment think of characteristic not 2. So I get q minus 1 by 2 elements. Generally in finite field, half of them are square, half of them are non-square, right? So I have q minus 1 by 2. And once I have chosen one of them square, I have to take one less for the lambda 2 square, that is q minus 3 by 2, right? And total half of the total thing. So I get these many of the form split regular semi-simple element. These are the one, these only these many elements I can get square. Similar kind of calculation I will do for anisotropic regular element, semi-simple element, and that I have to do in FQ square. So I will look at the square map at FQ square level. This will give me q square minus 1 by 2 of them are square, but FQ square star contains FQ star also, right? Because you know I hope that is clear to everybody. This is a simple field theory thing. So think about it. So it will contain FQ star because obviously something FQ square contains FQ first of all, right? So those half of them which have square root are already there. Something which doesn't have square root within FQ, they have square root in FQ square, right? Because they give you degree 2 extension, which is just FQ square. So this will contain whole of the FQ star. So I get q square minus 1 by 2. I don't want these ones because I'm trying to find the root for anisotropic regular. So I subtract q minus 1. And again, you have to do half because theta and theta bar will be conjugate. And which non-semi-simple are square? Again, it will depend whether lambda is square or not in characteristic 2. Right? So there are q minus 1 by 2. And if you compute all this and sum it up, this is the formula you get at the end. So if I want to look at GL2Q square, right? How many of them are square? What computation I wrote above, if you sum them up, you get 3 by 2 q to power 4 minus 5 by 8 q plus 1 by 8 q square plus 5 by 8 q minus half. For when it is even, you can sum it up and you will see that q to power 4. minus 2q plus 2q minus 1. If I want to look at the limit, I will get 3 by 8 and 1. So I get two different values here for square. There are two different kind of limits I can get. It will depend on what q is. Okay, what q is with respect to 2. So whether it is odd or even. So it is something to do with q and its relation with m. So if it is odd, I get 3 by 8. If it is even, I get 1. And you can also sum only regular elements. You can also sum only semisimple element. You can also sum regular semisimple element, and you'll get these numbers. But you will see one thing is that this 3 by 8 is everywhere here, and 1 here appearing here, 1 is also 1 here, here, here. So this is what the statement of the theorem said, that all these in limiting sense will give you the same value. So this also matches with, so this is the brute force method. Now let's look at our formula. Our formula was doing certain kind of sum over maximal tori. So how many maximal tori are there in GL2Q? There are two kind of tori up to conjugacy. So I'll call T1 to be the diagonal one of the kind. So there are two kind of maximal tori. One is the diagonal, which I have called T1. So this is lambda1, lambda1, lambda2, this kind of thing. So this is our T1. So if you look at cyclic structure, quite easy to see here. It's just CQ minus 1 cross CQ minus 1, right? So, but of course, like as Sripad was saying, that I can, for the Q being odd, I can further break into cyclic for the subgroup, but it doesn't matter at the end here. So I'll just think of it as a CQ minus 1 cross CQ minus 1. And while group for this will turn out to be, remember the normalizer of this is, so this will correspond to the symmetric group on two symbols. So that is 2 here. And for an isotropic torus, that is going to come from the from FQ square, right? The element some corresponding to an irreducible polynomial. So that gives me CQ square minus 1. And corresponding while group is cyclic group of order 2. So this is 2. And if you substitute in the formula, you have this equation 1 by 2 m comma this d1 d2. So m comma q minus 1, m comma q minus 1. For the second torus, it is 1 by while group, which is 2, and m comma this d here, q square minus 1. Right. So this is the formula. And let's check what value this formula takes if I substitute different values of q. You might find it confusing that I have taken limit q tending to infinity, yet I still have q in the expression, right? So, but you know that why this is coming. This is coming because of the cyclic structure. It actually vanishes because you are taking only a GCD with m. So it only depends on m. It cannot go bigger than m. Okay, so now what does that formula give value? So if q was odd, you will see that it will give you 3 by 8. So if q is odd, q minus 1 is even. So the first one will contribute 1 by 2 into 2 square. So that is 1 by 8. And this one will contribute only 2. So that will give me 3 by 8. If q is even, you'll get actually 1 because this is odd. So 2 comma q minus 1 is just 1, and 2 comma q square minus 1 is also 1. So half plus half is 1. So we exactly got the 3 by 8 and 1, which we had got by brute force method here. Yeah, so this explains the formula, and this explains also by brute force method that actually the formula is correct, at least in one case. You can compute also. I mean, if you feel happy to compute, you can try to compute for 3. In 3, you will get 3 different values, 1, 2 by 9, and 2 by 3. Q is 0 mod 3, Q is 1 mod 3, and Q is 2 mod 3, depending on that. And you can also do by brute force method, and you will get this kind of formulas for GL2Q cube if you want to take. And you see that we still get the same 3 values, 1, 2 by 9, 2 by 3. And you can also count regular, semisimple, regular, semisimple element, etc., etc. But I will leave this for you if you want to feel, if you feel like computing this sometime. Okay, so now what I want to do in the remaining time, I want to give you some idea of the proof for that theorem. I will take a small break and drink some water. If you have any question, you can ask me.
So Anupam, in this,
Yes, Smith.
if you fix a prime and then
Mhm.
take limit, q goes to infinity, then again you will have the same number of limit points.
Yeah. So it just depends on the p basically. I mean, q is p power something basically, right?
Yeah. Yeah. Initially, I thought maybe you are fixing a prime, but then whatever you did, that implied that you are not.
Q is p power something.
Yeah, but you are allowing p change.
Yeah,
Yeah.
the formula remains same. The formula can take different values. So there are two different kind of questions here. The formula is valid irrespective of you'll see from the proof, irrespective of what you are taking as q, because things appearing in the formula depend on the structure of g. Uh, I mean, even if you are seeing q there.
Okay. Thank you.
Okay, so let's move ahead. So these are some interesting results which I wanted to point you out, which I will also use a little bit, and you might find it interesting on your own. And uh, uh, let me just write them down first, and I'll try to explain at least one of them. So if I have a reductive group which is defined over finite field, then this is the result of Steinberg, that it gives you an estimate of the size of GFQ, the um, finite group of Lie type, which you obtain by uh, uh, like fixed point of some Frobenius map, and that is nothing but it is bounded between q minus 1 to the power dimension and q plus 1 to the power dimension. If it actually it's actually a corollary of the actual formula of GFQ. So Steinberg actually proved the actual formula of GFQ, which is kind of a little tricky, complicated formula. But from that formula, you can derive this as a corollary. Uh, but this is useful if you want to estimate something. Basically, in that sense, this is useful. But in general, it's good to know that how big is the size of the group GFQ, roughly speaking, and it is going to be just q minus 1 to the power dimension and q plus 1 to the power dimension. It's just between that. And another interesting result, which I will give you a brief proof of this, is that if I want to look at the regular semisimple element, how big is the size of regular semisimple element? So keep in mind, which I have been telling you, that if I look at the set of elements in G of Q, it is supposed to be polynomial in Q, right? So is it's also true for GFQ RS, that it's also polynomial in Q. So the thing is that there will be highest degree term, and there will be some lower order powers of Q, and that for that we can use big O notation basically. I mean, even if you are not familiar with big O notation, it just means that you are looking at polynomial, and then you have highest degree, and then you have some other degree, and that is, you say that O of that order basically, right? Because if you take Q very large, only the dominating term will matter. The lower degree power term will not contribute much in that sense. So this result says that GFQ RS is almost size of GFQ. It is 1 plus OQ inverse. Q inverse meaning 1 by Q. So it is of order 1 plus 1 by Q, and maybe some lower order term than 1 by Q, 1 by Q square or 1 by Q cube or something like that. Okay. So if you take Q tending to infinity, basically GFQ RS is just GFQ. Or if you take Q very large, that order Q inverse will not contribute. So probability of finding the regular semisimple element is 1. So in this is the density version of the statement. There are multiple proofs of this. There is also proof. I mean, it can be derived, I think, using Lang well estimate or something. But if you don't know that, there is also an easy proof, and I mean, little bit easy proof. And I'll just briefly present you this proof. This is in a paper by who? Maybe I'll write it later. Forgot to write here the reference for the proof. So this is the result. Let's say we want to prove, right? Uh, This proof will also tell you how to use things what you have seen so far. That is why I want to give you this proof basically. Uh, so if I want to look at regular semi-simple element in the group GFQ, I'm looking at regular semi-simple element. We know that regular semi-simple element belong to a unique maximal torus, right? So all I need to look at all maximal tori and regular semi-simple element inside those maximal tori, right? So I can simply write GFQRS is summation over look at a maximal torus and look at the regular semi-simple element inside this. So this could be simply written as TFQRS, right? This is what the meaning of this. And you vary over all possible maximal torus. Because regular semi-simple element belong to unique maximal torus, this is a full sum. You can't write this formula for semi-simple element because then semi-simple element can belong to more than one maximal torus, and then there will be repetition if you write this sum. Okay, so then you have to subtract something probably. So it will become a strange formula. But for regular semi-simple element, it's a very nice formula. Just sum over all maximal tori. Look at the regular semi-simple element in those maximal tori. Right? So I have this notation that this script T is basically the set of all F stable maximal tori in G. Okay, so the question of counting regular semi-simple element is nothing but count regular semi-simple element inside maximal tori and just sum them up. Okay, so now we'll try to estimate TFQRS. So first of all, if I look at the maximal torus TFQ, it has regular semi-simple element and something what is not regular semi-simple is basically not regular semi-simple. So I'll just write it as a sum of regular semi-simple and sum of non-regular semi-simple, right? The one which are not regular. So this is fine. I mean, this is just, writing as a two disjoint set. Now I want to estimate this. So I can estimate this TFQ using the Steinberg formula, which said that GFQ is size of GFQ is Q minus 1 to the power dimension of G and Q plus 1 to the power dimension of G. So here this can be applied to any reductive groups. It can be applied to maximal torus also. So it will turn out that GFQ is roughly speaking Q to power R. So Q plus 1 to the power R. R is the rank of the group G and Q minus 1 to the power R. So TFQ is of order Q to power R. So this will conclude that if I want to write in big O notation, TFQ is Q to power R, right? Maybe plus some small order term, Q to power R minus 1. This is what just, I mean, if I want to write, I don't want exact number, exact size of TFQ. I just want to use big O notation, but it is of the order Q to power R. So I want to compute this. So all I need to know is that I can estimate TFQ and RS. If I can estimate that, I'm done. Okay, so this was I will use the result what Sripad proved that if I have a regular semi-simple element, so if I look at the roots with respect to that maximal torus, then alpha will be always non-trivial if it is regular. So if it is not regular, that means there is at least one root which vanishes on that. Yeah, so I'm just using that. So that means to obtain non-regular semi-simple element, I can take subsets of the root system phi and find all possible, kernels of that, right? So let's denote dA to be kernel of some subset of roots, something like this. So let's write dA to be kernel of alpha, where what are the alphas I'm taking? Alphas are those which vanish on a given x, where x is non-regular. I'm given that x is non-regular. So non-regular will guarantee that A is non-empty, right? So DAFQ, and this DA is clearly defined over FQ. You can see that because it's kernel. So DAFQ is a subset of TFQ. The claim is this, that DFQ is of order Q to power R minus 1. because it is a proper, subset of TFQ. So dimension wise, it goes lower. It is one less dimension. It's a proper subvariety. Uh, use connectedness and all that. I mean, if you know a little bit of algebraic geometry, you can conclude from there. And that will say that if I want to estimate TFQ and RS, then I can take some or all DAFQ. But capital phi, the root system is finite. So there are only finitely many subsets A. So that finiteness will not contribute, which is independent of Q basically. So it will not contribute to any Q power. So hence it remains of the order Q to power R minus 1. Yeah, it will be some constant, and that constant will only depend on the basically the structure of the group G, because it depends only on the root system. So that it will depend on that constant. And hence, now combined with the earlier thing here, this equation here, TFQRS is of order TFQ and TFQNRS. So you will see that TFQ regular semisimple is of the form Q to power R plus something of order R minus 1. Now to get GFQRS, I have to sum it over all such maximal tori. And if I want to sum over all maximal tori, I have to multiply by the number of maximal tori. And this is again a result of Steinberg, and it's there's a proof in Karta's book that number of maximal tori is Q to power 2n, but n is the size of positive root system. And from there, if you substitute that, you'll simply get that equation what I wanted. The size of regular semisimple is roughly of order the group GFQ plus something of order Q inverse. Yeah, this is a very nice proof, and we use basically this strategy only to prove for power map and try to determine regular semisimple element using this method. Okay, so let's try to see how we can carry forward the proof for the theorem which I said. So this was the theorem, just to recall, and this is what we want to prove. I will give you a sketch of the proof for regular semisimple element, basically, that if I want to look at regular semisimple element, I'll give you an idea that this quantity will give me this quantity. This is equal to this. And it's not very difficult from there to actually, using the density argument, it is not difficult to prove that this quantity is equal to this, and equal to this. So the main step is to prove that this will be equal to this formula. Okay, so here is a sketch. So I will claim that, so this is the lemma, I will claim that GFQ to the power m regular semisimple element divided by GFQ is given by this sum plus something which is of order Q inverse. Okay, so that if I took limit tending to Q tending to infinity, this term will not contribute, or Q inverse will not contribute anything. So I'll get the formula what I want. So this is what I want to prove, right? Okay, so just recall what we said, that regular semisimple elements. So remember, I am going to work with the regular semisimple element here. That's why I've been emphasizing regular semisimple element. Regular semisimple elements are something for which connected component of centralizer is a maximal torus. So these belong to a maximal torus, in fact, a unique maximal torus. So regular semisimple elements are dense in GFQ, which is what I just gave you a proof. The GFQ RS is GFQ 1 plus OQ inverse. Okay, so where do we find regular semisimple elements? So as I said just now, that regular semisimple element belong to maximal torus. So we work with maximal tori basically. Yeah, and in fact, it belongs to a unique maximal torus. For example, for GL and Q, we know what kind of maximal tories are there. They correspond to partition of N. I think I will write it down towards the end, maybe as an example of GL and Q. Okay, so it boils down to finding an estimate over maximal torus. I reduced the problem to compute something for GFQ regular semisimple to various maximal tori, because regular semisimple element belong to unique maximal tori. So on maximal tori, I can take power and sum it up, right? So that's what I'm going to do. So I fix this notation: T is T bar FQ, maximal torus in GFQ, where T bar is some f stable maximal torus. Then I look at T intersection GFQ regular semisimple element, right? So this is of order q to the power r plus OQR minus 1. Because this is just size of T. I mean, size of T itself is q to the power r. So this statement is, I mean, the second statement is nothing big deal. It's not saying anything new. But what I'm interested in looking at is T to the power m intersected with GFQ regular semisimple, right? So that I can take sum over this to get everything for GFQ. And this is basically looking at T to the power m plus something OQR minus 1, right? And for T, which is abelian, so on abelian group, if I look at the power map, it is basically a homomorphism, and kernel will be obtained by looking at the cyclic structure of that group and looking at m comma d1, m comma d2, and m comma ds, right? So this is where that, d1, d2, ds appear here. So I get this. Then to get the final total number, I have to look at GFQ RS to the power m by GFQ. So I look at the numerator. Numerator is basically saying that I can look at over all maximal tori and sum them up. And that is T to the power m intersection GFQ RS. But this estimate I have got here as this quantity T by MD1, MD2, MDS plus OQR minus 1. So I just substitute that here. And once I substitute that here, this sum is over all maximal tori. So now I want to reduce it to up to conjugacy. If I want to work up to conjugacy, then I have to multiply by the number of conjugate of maximal tori. So which is what I have done. Multiply by GFQ by normalizer of T. And now then the sum will run only over non-conjugate maximal tori. And a little bit of manipulation will give you. So now GFQ order will get cancelled. So normalizer will go inside, and that will give me order of the while group because you have this order of T here. And in the second sum, I have 1 by WT T. You see here that WT does not depend on Q. It's a while group. It depends on the structure of G. So there is no Q appearing here. So this is just some kind of constant. T is roughly of order Q to the power R. So that will give me Q inverse. So this is what happens at the last step, and that gives me the formula. Yeah, so I will not go into further detail. I just gave you a rough idea of how the proof goes. Instead, I will just, okay, I still have 10-15 minutes. So instead, I will explain you briefly that how I can apply this for at least one example. We have worked out for GLN and unitary group and SLN in the paper. You can look at that. But here I will just tell you how to work for GLN. Okay, and that will also tell you some properties of GLN in some sense. So maximal GLNQ, basically we are looking at the n by n invertible matrices over finite field FQ. Maximal tori in GLNQ, these are in one correspondence with partitions of n. Okay, so if I take a partition of n, which is n1 plus n2 plus ns, then the associated maximal tori is something like this. How do we visualize this? So I have this n by n. So suppose I take the partition of n to be 1 plus 1 plus 1, all 1. Then the corresponding maximal torus. So, I mean, I'm not giving you proof, but I'm telling you as a fact, and this can be useful for you if you want to work with these groups. So it's good to get working idea. And this kind of classification for maximal tori are there for certainly very well explicitly written for all classical groups and things like that at various places. So let's just see how it looks like for GLN. So if I look at the partition 1, 1, 1, 1, then it is nothing but the 1 by 1 block on the diagonal. So lambda 1, lambda 2, lambda n. So this gives you nothing but the diagonal torus, right? What happens if I have a partition where, I mean, other than 1, something else appears, right? Suppose n equal to 2 plus 1 plus 1, and these ones are n minus 2 times. So of course, for these ones, again, this lambda 1 It's a lambda 3 up to so on lambda n appears. And now there is a 2 by 2 block here. What is this 2 by 2 block here? It will correspond to an irreducible polynomial of degree 2. So this is n isotropic maximal torus in GL2 basically, which we have been like, we saw in GL2. This will correspond to FQ square star. So you can take a regular semisimple element basically and take polynomials in that. Take a degree 2 reducible polynomial basically and look at its companion matrix and look at all polynomials in that. That is what is FQ square star. So you can explicitly write down what this is, and this is nothing but isomorphic to FQ square star. So in this case, so in the first case, the torus is FQ star cross FQ star n times. In the second case, it is going to be FQ square star and then FQ star cross FQ star cross FQ star. In general, if I have partition which is n1, n2, ns, then for each n1, there is an irreducible polynomial of that degree, and take the companion matrix of that, and then look at the polynomial in that companion matrix, which will turn out to be isomorphic to fq to the power n1 star, basically, right? And that is what is this. So this can be written very explicitly what I have the way I have described here. I mean, it's very concrete description of this. And from here, you can also, at least in this case of GLN, it is quite easy to write, as a cyclic group, product of cyclic group. You can simply say q to power n1 minus 1, q to power n2 minus 2 minus 1, and so on. And then if you need to factorize further each one of them, you can do that. But there is no need in general. Another thing which we need in our formula is the size of corresponding while group, right? And again, this is something well known. And again, I will describe you what happens. So there are two ways of writing a partition, right? Either you write it as n1 plus n2 plus ns, or you combine if something repeats. So that combine one repeats m1 times, then I will write 1 to power m1. That means basically 1 plus 1 plus 1 m1 times. So there are two ways of writing a partition. So here I'm writing in the second one. Uh, uh, you also know that the partitions of n also describe conjugacy classes in the symmetric group Sn. And the symmetric group of Sn is basically the while group of the GLN over K. So obviously symmetric group is going to play a role here. So what you do is that look at the partition of lambda, which is 1 to power m1, 2 to power m2, and so on. Write down the associated element in the group Sn, right? There is a element in Sn corresponding to every partition, standard element or whatever you want to call this. And the while group is nothing but the centralizer of that element in Sn. It's isomorphic to that. So, but all I need is the size. So I can just compute the size knowing this, basically. Right? So the size will turn out to be, if I'm given lambda is 1 to power m1, 2 to power m2, n to power mn, then the size will turn out to be factorial mi, I to the power mi, and their product. This is what the size will turn out to be at the end. And there are a bunch of other notations which I need. I will explain you once I write the formula. So now knowing these things for GLN, I want to plug in this in our formula. Remember our formula was somewhere here only. I will show you this formula again. So yeah, this formula here. So to compute this for group G, I needed to know all maximal tori, and I need to know their cyclic structure D1, D2, ds, and compute while group, right? So this is what I have described for GLN. So for GLN, I have described a cyclic structure for each maximal torus. I know all maximal tori up to conjugate because this sum varies over all maximal tori up to conjugate, non-conjugate maximal tori. And for each one of them while group, I know all this stuff. So I can just plug in this formula to get for the GLN. And so this is what I write here. So I just, that quantity I just denote by P, GLN, QM because it will, for GLN Q, it will depend on N, Q, and given M. So I just have given a symbol for that. P is for probability of finding that. Okay, so for the group G, GLN, if you, and for M prime, there is a nice formula. So let's take M to be a prime. if M divides Q, then this is always 1. And if MQ is co-prime, MQ is 1, then this gives me this formula. Summation over all partitions of N. So this reflects the non-conjugate maximal tori. Here the non-conjugate maximal tories are determined by the partitions of N. So there is no surprise in that. And then 1 upon while group. So that second thing is here, centralizer of so mark here. So this is the while group. So 1 by centralizer of sigma lambda in symmetric group, that size. And remember the GCDs of M comma D1, M comma D2, and so on. What is that? Then that can be simplified into this number, M OQ lambda. So this is capital M to the power pi something OQ and partitions. So there is a function on partitions, and that will determine this number of powers, what powers to appear. And that is nothing but, that can be pi OQ lambda can be simply described here, is that, sum of all those powers where that B divides that I, right? Just take the sum of those powers. That is what is the value of pi B lambda. And OQ meant is supposed to be like, order of Q in Z mod M Z star. So basically I need to compute this value for only something in Z mod M Z star. So this can take at most M minus 1 values, right? This power can take at most M minus 1 values. And that gives you that finitely many values here. In fact, it can be said precisely that total value will be 1 plus nu M minus 1 for GLN. And what is nu M minus 1? This is nothing but set of all those A which are between 1 to N, and A divides M minus 1. It can be just said very precisely. We also have similar formula for unitary group, and but I have not written here, but you can have a look at that. Yeah, I still have 5 minutes, but I think I will stop here, and if you have any question, we can discuss something. Anybody has any question or comment?
So, Anupam.
Yeah, Shushil.
So, if you so you are varying Q. Now, if I fixed Q and vary M, then this will be again finite value, the quotient limit.
So there are several things to vary here. Yeah, we are not thought of. I mean, other things are more tricky to see. If you vary M or you vary N, we were trying to look at varying N. That is, I think, more important problem generally from the combinatorial point of view.
Okay.
See. But there is no definite answer.
Okay. So we don't know whether this number will be finite or not. So yeah, and
yeah, and so they're not just finite. We also want some nice formula. I mean,
right. Okay.
If we can get some nice formula, we have also written down some kind of generating function to get these values limits. This can be actually computed from knowing that generating function. You can get this coefficient. This has a coefficient of that. Yeah, but certainly n varying is one of the important thing, and of course m varying how much it changes and things like that.
Also, in the beginning, you said that you are taking the power m and then looking at the intersection with the regular semisimple element. So, if I take a regular semisimple element and take the power, so is there any containment that will?
So the limit, in limit they are the same. In general, it is contained. It is generally a subset, probably, in the image, because if you take regular semisimple, its power may not remain regular. So it might become a smaller subset than what we are looking at. Okay. But it's not very difficult to prove that if you want to take limit Q tending to infinity, if you make Q very large, the two things will turn out to be same.
Okay.
So if you take Q large, then even all those thing. I mean, you look at regular semisimple element and its image, you look at semisimple and its image, all those things turn out to be same, basically same as this.
Okay.
But definitely, if you want to look at individually, they are going to be different numbers.
I see. Oh, okay, nice talk, Anupam.
Okay, thanks.
So Anupam, if for M we suppose we don't take all the integers, we suppose we just take powers of a fixed prime or something, then is something known.
M, if you take just power of, so this
Some
is what
prime or
I
some number.
to at the end wanted to write this for M. If you take just a prime, there are neat formula.
Okay.
Yeah, I mean, of course, if M is like product of more than one prime, then this kind of formula will become more tricky to write.
Yes, yes, yes. Yeah, I was expecting maybe there would be something for if you take powers of prime, which you are saying is there. So
Mhm.
good. Thank you.
Yeah, maybe for just a power of single prime, you can write formula like this. But certainly, if you take more than one prime, it will become more tricky to write the formula.
Okay. Thank you.